Hello everyone, and welcome to another video lecture on trigonometry. Today we are focusing on solving trigonometric equations, and our video is going to sit somewhere uncomfortably between a full lecture video and supplementary notes for my USF students. On the one hand, we are going to give basic information and reminders, kind of like the fact that you can see partially on the screen. We are also going to do a couple of basic problems just to make sure we can get our eye in, we can practice using the techniques. Even if you've been in my class, it should be good for you as kind of a warm-up. However, after that, we are going to delve into the more challenging problems from solving trigonometric equations. So my recommendation is make sure that you practice the basics, even in addition to what I'm going to do, before you get into the material with me. So, starting with this basic fact that you have here on the screen, we have basic equations for sine, cosine, and tangent. These can all be pretty much derived from a sketch of the unit circle. I'll show you what I mean by that. So if I were to sketch the unit circle just roughly like so, and I highlight the quadrantal angles at 0, pi over 2, pi, and 3 pi over 2, or if you prefer at 0, 90, 180, and 270 degrees, you can pretty much see how these things emerge. For example, sine of theta is equal to 0. Well, we can tell that sine of theta is going to be equal to 0 whenever the circle touches the x-axis, because that's when the y-coordinate of points on the circle is 0. That means we're looking at 0 and pi if you are in the first unit circle. And if you want to get the general answers, which is what I've written down, you would simply notice that as long as you take pi and multiply it by a whole number, you're going to wind up at one of these 2 points. And so therefore, the answer is, in general, theta will be equal to n pi. On the other hand, sine of theta equals to negative 1 happens in the first unit circle down here at 3 pi over 2, 270 degrees. And after that, you would have to find an angle which is coterminal with 3 pi over 2, which is why we have 3 pi over 2 plus 2n pi. Similar analyses can be done for every single one of these equations, for sine, for cosine, and for tangent. The big difference for tangent is that we have to also include the points that go along with negative 1 and positive 1, which you'll notice are not quadrantal. They're based upon the reference angle, pi over 4. Now, as mentioned, these are probably the most basic trig equations you're ever going to run across. Most of the time they're going to be a little bit more challenging than this, so let's give ourselves a little space and we'll start considering a more challenging situation. So, we consider an equation that looks like sine of theta is equal to r. We are assuming that r is in the closed interval negative 1 to 1 because otherwise this equation doesn't make any sense. Then we can do the following in order to solve it. So, first of all, we notice that alpha, which is an angle I'm going to get by taking arcsine of r, is an angle in the range of arcsine. And for those of you who do not remember what the range of arcsine is, that's not too hard to reproduce here. It turns out the range of arcsine is the closed interval from negative pi over 2 to pi over 2. And we're going to think of alpha as being our very first solution to this problem. The reason for this is, as we should know by now, if alpha is the arcsine of r, then there is a related equation that goes along with it, which would be sine of alpha is equal to r. So that is one solution. And there are two ways that this solution could look visually, which is going to be important to us. In the situation that r, the number on the right-hand side of our original equation, is positive, then we wind up with a situation where alpha is going to have to go into quadrant 1. After all, alpha has to be either in quadrant 4 or quadrant 1. That's what our range here says for arcsine. So it must go into quadrant 1, which will put it looking something like this. After that, we know that there should be one more solution. The other solution will be because of reflections. I happen to know that sine is a function that does not change under y-axis reflections. So, if I draw another angle across the y-axis, the reflection of my original one, and I will get an angle that has the same reference angle as our original, that would be our second angle. The other situation would be if it turned out that r was less than 0. If r is less than 0, so we have a negative, then alpha is going to have to be in quadrant 4. Actually, it's going to be a negative angle, which means that would put it somewhere down here, like this. And then, once again, we can use our reflection properties for sine and notice that another such solution would be over here. And this angle will also be based upon the same reference angle as the one in quadrant 4. I haven't handled the situation when r is equal to 0 here because we already did that above. For every other case, this is more or less what we would expect from our picture. These solutions also then lend themselves to formulas that we can use. It's easiest to see it when we look at the r is greater than 0 case. So if this angle is alpha right here, you'll notice that the angle in quadrant 2 is going to have a reference angle of alpha, and so that means that the second angle that we are looking at, the one in quadrant 2, it must be given by pi minus alpha. If we wind up in the blue case, we can also make an analysis that it will be similar. Since this is alpha, a negative angle, if we were to take pi and subtract alpha, we'll wind up with an angle that's just a little bit bigger than pi. In fact, it will be an angle that should be in quadrant 3. That is the second angle that we came up with in our second case. Either way, we have now found that there should be a predictable system of equations for our angle theta in this situation. The first part of our system of solutions should be theta is equal to alpha, or, because of coterminal angle properties, any angle coterminal with alpha. If you like to work in degrees, this would look like alpha plus 360n instead of 2 pi n. The other one would look like pi minus alpha plus 2 pi n. And these would represent all possible solutions for the equation sine of theta is equal to r. We can do the same thing for cosine. Starting with the equation cosine of theta is equal to r, again, r has to be between -1 and 1, these are sine and cosine. We would follow a similar procedure. The difference is that now we would need alpha to be cosine inverse of r, and we're going to get an angle to begin with, this alpha, which is going to be in the upper half circle between 0 and pi, and once again we can break it down into the two basic situations. The first, when r is greater than 0, gives us the two angles we show here. Alpha will be in quadrant 1, which is predictable. The second angle, the one that is a reflection of alpha, will be in quadrant 4 because cosine does not notice reflections across the x-axis. It turned out in a case like this that this angle below the x-axis is going to be written as 2 pi minus alpha, which makes sense based upon the reference angle that we're showing here. If it should happen that r is less than 0, then because arc cosine only gives us angles in the upper half circle, our first angle, alpha, must be in quadrant 2. If we reflect, we're going to reflect down into quadrant 3, and once again, a little bit of calculation will wind up showing us that the second angle is given by 2 pi minus alpha. And once again, we can turn this into a system of solutions. There are many similarities between what we've written now and what we wrote before, but one thing I want to go ahead and draw your attention to is the symmetry. When we are talking about the solutions that we get, the table of solutions that we would get, which we can put together in just a few minutes, we always rely on symmetry to produce this second result. So, whereas when we were working with sine of theta equals r, we had a first line of alpha plus 2n pi and a second line of pi minus alpha plus 2n pi, this time, because the symmetry has changed, we also change the second line to reflect that symmetry. We have to do that and to make sure that we're following the behavior of the trig function. We're going to see another change kind of like this for tangent as well, and tangent is going to be probably the most strange of these three that we've seen so far. And I suppose it's time to move on to tangent. I mean, we can't exactly call tangent out and not at least represent it, so here it is. If we have the equation tangent of theta is equal to r, now here's the very first change. Tangent goes from negative to positive infinity, so we no longer need restrictions like we did for sine and cosine. R can be any number. If we have an equation that looks like tangent of theta is equal to r for any number r, then we would take arctangent of r to give us alpha. It's going to give us an angle, once again, in the range of arctangent, which is similar to sines. The difference is we have to leave off negative pi over 2 and positive pi over 2 because they are vertical asymptotes for tangent. And then we're going to get pictures that look kind of like the following. As I'm sure you all can expect, the very first time that I draw alpha with r greater than 0, we're going to get a quadrant 1 angle. That is not at all surprising. You'll notice that I've drawn this r greater than 0 kind of cattywampus. It's diagonal, I suppose, if you want to be less weird with your terminology. That's not on accident. That is because tangent is symmetric through the origin. It has kind of a diagonal symmetry. In other words, if I were to do two reflections, first across the y-axis and then across the x-axis, I will wind up with an angle which gives me the same value in tangent. So my picture actually follows the diagonal line that I've indicated here. And we will find out that this angle down here is going to be exactly pi plus alpha, which is evident from the reference angle that we're drawing in here. Drawing the second case, if it turns out r is negative, then kind of like with sine, our first result should be an angle down here in quadrant 4, and then if we follow the exact same sort of diagonal symmetry we did in the previous case, we'll get an angle up here. This one will be alpha, and this one will be pi plus alpha, or alpha plus pi, however you prefer to show it. This leads to the following air quotes system. I say air quotes for system because in this particular case there are not two branches of solution. There's only the one. If you go back and look at cosine for a second, because that one is close to hand, we wound up having two branches because of the way cosine symmetry works. Whether r is positive or negative, we wind up with these two branches, and so we have to have two branches in our solution for theta. However, here, every time that we figure out what r is, every time that we are given an r would be the better way to say that, we wind up with only one branch. You are along this one straight line or that one straight line, and all of our answers are related by half-circle rotations, this n pi. Because of that, we don't need to draw more than one branch of solution. We only need the one, and that makes cosine and sine very different from tangent. Okie dokie, that's enough theory. Let's go ahead and do some examples. That's what we really need to do to clarify everything, and we are ready for some basic ones. Remember, these are kind of like a warm-up if you're one of my USF students, and for those of you who are not, well, start with these as a warm-up and then do more of them, as many more as you possibly can. Here we go. We are going to solve the equation tangent of theta is equal to root 3, and we're going to do it in 0 to 2 pi. In other words, in the first full circle. We may as well go ahead and draw a picture of this first, and luckily we have the basic sketch of what to expect up above, so it should be pretty straightforward. Hopefully there's no debate on the fact that root 3 is a positive number, so that means that we're following the red case. We have an angle in quadrant 1, that'll be our alpha. We have an angle in quadrant 2, that'll be alpha plus pi, which is one of the additional angles. We know basically what to expect from our answers, now we just need to know what alpha is. As a little reminder, one of our essential angles in quadrant 1 that we know is pi over 3, and it has a terminal point of 1/2 comma root 3 over 2. If I calculate tangent of pi over 3, Since we know that tangent is always given by the y-coordinate divided by the x-coordinate, that would be root 3 over 2 divided by 1/2. And a little bit of simplification should quickly convince you that the answer is root 3. This must be our answer. In fact, and this is an important thing to point out to everybody, if I find an answer in quadrant 1, which is part of the range for arctangent, which gives me the right answer, then arctangent is going to be exactly the angle that I worked with. So in other words, what we are saying here is pi over 3 is equal to arctangent of root 3. From here, we can get all of our solutions. We know all solutions should look like theta is equal to pi over 3 plus n pi, but we want only solutions in 0 to 2 pi. Looking at our picture, there should be two. There should be the first one that we came up with, that would be the pi over 3, and the second one we should get would be when we take pi over 3 and we add pi to it. In other words, and I'll go ahead and put this here because this will make your life easier later on, that means we want this solution when we let n be equal to 0, because when n is equal to 0, we wind up getting theta equals pi over 3 only. And the second one that we get is when n is equal to 1, because when n is equal to 1, we get theta is equal to pi over 3 plus pi. And I'll let you double check this for yourselves, but pi over 3 plus pi should be equal to 4 pi over 3. Normally, once we've gotten our answers like this, especially if you're putting them into Pearson or similar homework software, you're going to write the solution set, which I'm just going to write as sol set here. This set has sol, 2 sol, and those 2 sols would be pi over 3, comma, 4 pi over 3, contained in set builder brackets, and that is it. Let's do another one. We're going to solve sine of theta is equal to, whoops, let's make this a negative. We want to make things a little bit more interesting. So this will be a negative root 2 over 2. There, that looks better. You'll also notice one other small thing. In the previous problem, I said solve tangent equals to blah, blah, blah in 0 to 2 pi. Here I haven't done that. We're only going to give the general solution rather than specific solutions, which will be enough because there's actually a consideration we're going to have to take into account. Let's go ahead once again with the picture first. Since the right-hand side of our equation is negative, this implies we're in the second case, which means that we'd expect one of our answers to be down here. This is going to be our alpha. And then we're going to have our second one over here. And if you remember, this is going to be our pi minus alpha. Now, when we're working on a problem like this, a lot of times I like to go back to quadrant 1, even though I know we're dealing with a negative number here. The reason being, when we are getting this angle alpha, remember that we are going in the negative direction. So if I were to find a quadrant 1 angle that did the job, then alpha would be the negative of that quadrant 1 angle. Excuse me. Let's say that again a little bit more clearly and with a little less rolling. If we can find a quadrant 1 angle that does the job, alpha will be the negative of that quadrant 1 angle. And so that will make our job a little bit easier. You probably already know which quadrant 1 angle I'm going to call upon, but I may as well draw the picture here. Consider this a reminder to know your basic angles, a second reminder, I suppose, but pi over 4 is a quadrant 1 angle which has a y-coordinate, in other words, a sine, of root 2 over 2. You may be interested in seeing the calculation here, so I'm going to go ahead and do that. If I were to take sine of negative pi over 4, which is what I claim is the correct answer for alpha here, then we can use the even-odd properties and notice that sine, as an odd function, will spit out the negative. And now we can go back to using pi over 4 and its y-coordinate to find out that this will give us negative root 2 over 2. Once again, we have found an angle that does the right job, and it is an angle in the range of arcsine. So what we are learning from this is that when I take arcsine of negative root 2 over 2, the answer must be negative pi over 4. If we follow the information that we put up previously, that would lead us to say, okay, well, theta must be equal to, let's see, negative pi over 4 for the first one, and then plus 2n pi. And then for the second one, we're going to take pi and subtract negative pi over 4, which really means the same thing as pi plus pi over 4. So that should give us 5 pi over 4 plus 2n pi. And now this is the correct answer, but, and this is a rather big and hairy but, so please pay attention, but even though this is technically the correct answer and may get accepted potentially, usually this is not the format that we want our answers to be in. Why? Well, generally speaking, we really want these first two pieces of both lines, the first angle plus 2n pi, the second angle plus 2n pi, we want the first angles to always be positive angles if we can help it. Now you'll notice in our picture here that 5 pi over 4 is okay. That would be if we wrapped around the circle to the blue line in quadrant 3. However, negative pi over 4 is our first line answer, the basis of our first line answer, I suppose you could say, and it goes in the negative direction, which isn't really what we want. What we want is an angle that stops at the same line, in other words, a coterminal angle, that goes around in the positive direction. Luckily, though, it's not hard to see what that answer should be. You'll notice from our previous work that what we have said is that the reference angle for alpha is pi over 4. In other words, if we were to follow this line that I've indicated counterclockwise around to where alpha is, we would stop pi over 4 short of the positive x-axis. And so that suggests that we can rewrite our answer as follows. So now it says 7 pi over 4 plus 2n pi and 5 pi over 4 plus 2n pi. This is the typical way we can write this. It's the typical way we want it. And we can write it this way because, as I'll put down here, just so that way we have a written record of it, because 7 pi over 4 is a coterminal angle to negative pi over 4. Specifically, it's negative pi over 4 plus 2 pi, which makes this okay. An important note to go along with this is that whether you gave the first solution bunch, the first solution system that we used, or whether you give the second, it will give the right answers. However, the second one is more typical, and that's the one that I want you guys to concentrate on finding. And lastly, before we move on to the more challenging problems, I may as well go ahead and make a side note. Some students do prefer to work in degrees rather than in radians. I always encourage everybody to learn how to do both systems well. But what that means is, if I've been doing a lot of work in radians, I should show it to you also in degrees. So let me indicate to you where the changes would be. The first big change is obvious. Instead of writing pi over 4 here, we would be writing 45 degrees. That would mean that whenever we wrote negative pi over 4, what we really mean is negative 45 degrees. And where we write 5 pi over 4, or in other words, start at pi, 180 degrees, and go an additional 45 degrees, we would be taking 180 plus 45, which would give us 225. The portion that says plus 2n pi, well, 2 pi is 360 degrees, so what we would write instead is 360 degrees times n. If you want to see the final result, we simply scroll down a little bit and we can see it here. Instead of 7 pi over 4 plus 2n pi, 5 pi over 4 plus 2n pi, we would have 315 degrees plus 360 times n, or 225 degrees plus 360 times n. You could also get these results if you simply took all the answers that we got in radians and multiplied by the standard conversion rate of 180 degrees over pi. All right, enough of these nice, simple, friendly problems. It's time to have some that have teeth. So let's go ahead and put a brand new and slightly more challenging problem up here for us to work on. Here's one a little bit more to our liking, quote unquote. We are going to solve 2 times cotangent of x plus pi over 6 plus 2 is equal to 0, and we're going to do this in 0 to 2 pi. Now you'll notice a couple of things. First of all, we are working with cotangent, which is not one of the functions we've figured out how to solve already. People in my class probably already have an idea of what we're about to do with that, but we're going to have to deal with the fact that this is cotangent and not sine, cosine, or tangent. It will make a difference. Another thing is that we are dealing with 2 times cotangent plus 2 equal to 0, not a nice straightforward equation like function equals blank. So the first thing we should do is we should isolate the trig function. We want to wind up with an equation that looks like cotangent equals something first, and then we'll deal with the cotangent. So I'm going to write everything down, and we're going to make some quick changes. I won't spend too much time on those because I think probably you guys know how to do the basic algebra that I'm going to suggest. We move 2 to the other side of the equation by subtracting it from both sides. That gives us this step. We divide both sides by 2, which brings us to the last, supposedly, intermediate step. Now we have an equation that looks more like what we would expect. It is a trig function of an angle is equal to -1. We do need to change things around a little bit, so we're going to appeal to a basic fact. We know that cotangent and tangent are related by a reciprocal identity. A reciprocal identity that I wrote up on the screen for those of you who just said, huh? We know that cotangent of an angle is exactly the same thing as 1 divided by tangent of an angle, as long as tangent is not equal to 0. So because of that, we can also change the equation the following way. By switching from cotangent to tangent, we would then also take the right-hand side and look for its reciprocal. In other words, for 1 divided by -1. In our particular case, that's easy. It works out to be -1. So that's a nice sort of happenstance for us, but generally speaking, you're going to have to do what we did here in the middle and look for a reciprocal. Now we are looking at an equation that we know how to solve. We have tangent of an angle, we'll discuss it a little bit more in a minute, is equal to -1, and we know how to solve this. In fact, it was one of the basic facts that we got at the beginning. The form of this equation implies that what we must be getting would be something like, well, let's see, should be either -pi/4 or, if we want an easier one, 3pi/4. Either one is okay. I've included the sketch here to justify that, but we said 3pi/4 on the first page, and it does make things a little bit more consistent with our previous problem, so we'll leave it that way. 3pi/4 plus n times pi, which is the period of tangent. And you would think at this point, based upon how we solved the previous problems, that now all we'd have to do is figure out which answers that corresponds to in 0 to 2 pi by letting n be different values of a whole number. But that would be forgetting one important step. And that important step is, when we are solving the equation that we wrote up here, tangent of this whole angle, x plus pi/6 equals -1, the solution that we've put down here says x plus pi/6 ought to be equal to 3pi/4 plus n pi, which is not exactly what we want. We want a solution that's about x only, so we're going to have to do a little bit more algebra and move pi/6 to the other side of the equation. That means we should get an equation like x equals 3pi/4 minus pi/6 plus n pi. And now, noticing that both 3pi/4 and pi/6 have a least common denominator of 12, we can simplify as follows. Feel free to check my arithmetic there if you're not 100% certain. However, assuming we haven't made any mistakes, we then get the following solutions by taking different integer values for n. First of all, if we allow n to be equal to 0, notice that all we'll get from our solution is 7 pi over 12, and 7 pi over 12 certainly is one of the possible answers in 0 to 2 pi. In fact, it's an answer in the second quadrant. So we'll write that down right here. The second should be if we take n equal to 1. If we do that, we're going to find that x is equal to 7 pi over 12, just like before, but now we're adding pi to that. And after a quick combination of these two numbers, we should be getting 19 pi over 12. Okay, everything looks good, so now we're just going to scroll down and we're going to say the solution set, the sole set for us, will therefore be 7 pi over 12, comma, 19 pi over 12, and this concludes the problem. Now, I know what you're thinking after a problem like that. You're thinking to yourself, sir, may we have another? And of course you may. In fact, let's go ahead and do this one. It's a little bit different than we had before, and also it has a funny little mistake. This thing should be equal to 0. Gosh darn it. So we better make sure it says that. So we have solve the product of these two pairs of parentheses equals to 0, and we're going to do that in the first full unit circle. Well, we're going to have to do something a little bit different and interesting here. So let me go ahead and do that different and interesting thing by an observation. I'm going to put it underneath. I'm going to write recall. Recall, if I take two numbers, or yeah, two numbers is fine. Two expressions is also okay, but we'll say two numbers, a and b. I multiply them together, and the result is 0. Then automatically, we know something about either a or b, or possibly both. Either a is 0, or b is 0. I'm not excluding the possibility that both happen here. A lot of times you'll hear folks call this something like the zero factor property, and we're going to use it in this problem. Specifically, I notice that I have a factor, this will be kind of like our a, times another factor, our b effectively, and it's giving us 0. So, following along with the zero factor property, we may as well take both of these terms and set them equal to 0. Starting with the first and employing just a little bit of dark magic, we wind up with the following simplified equation. And while we're here, we may as well go ahead and make an observation. Hopefully you guys have been practicing your basic angles well enough to notice this as well, but you'll notice, and I'll put this here in parentheses, notice or note that sine of pi over 3, so that would be sine of 60 degrees for those of you who prefer degrees, is equal to root 3 over 2. So that's giving us a clue here of what to expect. And for good form, I'll go ahead and say underneath pi over 3, 60 degrees, just to make sure we remember it. Now we can move on and do the same thing for the other part of this expression. And a little math magic later, we get cosine of theta is equal to 1/2. And we can make another note here. Note that cosine of pi over 3, so once again, cosine of 60 degrees, is equal to 1/2. It appears then that we are getting similar answers, or at least similar beginning answers, to our work for both of these factors, which is interesting. We may as well go ahead and take all this information and put it together into a picture to help us figure out what to do from here and how to put our systems together. I've completed the sketches for both of the solution systems that we'd expect. I'm keeping it color-coded, so everything in red goes along with sine, everything in blue goes along with cosine, and notice we have a little bit of overlap. Both of our systems of solutions give us 60 degrees, pi over 3 in quadrant 1, but after that they disagree. Sine is going to give us an angle in quadrant 2 additionally. Cosine is going to give us an angle in quadrant 4 additionally, and this makes sense given their behavior and their reflection properties. We can now go ahead and put down the systems a little bit more algebraically. Again, color-coded. These systems, just like the pictures we drew, come from our previous work, and so now the only thing left to do should be to let n take on different values, and we'll see what we get. So let's go ahead and start with n equals 1. Now, if we allow, or I'm sorry, it shouldn't be n equals to 1. I'm getting a little ahead of myself here. I'm just so excited to work on this problem. Let's let n equal to 0. Got to start somewhere. So let's see, if n equals 0, which is probably the easiest value of n to begin with anyways, you'll notice in the red system we wind up getting theta is equal to, well, let's see, pi over 3 from the first branch, and 2 pi over 3 from the second branch. If we then put it into the second system, I'm just going to go ahead and keep listing them along the same line of equation here. Let's see, we would get pi over 3 again. That's a repeat. We really don't need that one. And then we would get 5 pi over 3. Now, we don't need this one, as we already mentioned, so I might as well go ahead and strike that from the record. In previous problems, though, specifically in problems where we've had to deal with tangent, we've had to use some other values of n. So why don't we go ahead and try a few others just to see what happens here. In particular, since I was so eager to let n be equal to 1, why don't we try n equals 1? But you're going to see very quickly that this gives us issues. For instance, when I put n equals 1 into the first line of the first system of solutions, I get pi over 3 plus 2 times 1 times pi, or in other words, plus 2 pi. Now, that's bigger than 2 pi. It has to be. 2 pi plus additional, that's definitely bigger than 2 pi. That's an issue. So I'm not even going to consider simplifying this at all. It's a problem. Similarly, if I go into the second branch, I'm going to get 2 pi over 3 plus 2 pi, which is also bigger than 2 pi. So that's another problem. Neither of those can be considered. If I go into the next system of solutions, I would get pi over 3 plus 2 pi. Again, not only is it redundant, it's also no good. And we would then get 5 pi over 3 plus 2 pi. Every single one of these is bigger than 2 pi. So, first thing we can learn, letting n equal 1 is not going to do us any good. It gives us solutions that go outside of the first full circle. So we're going to ignore these. We're actually going to scratch them out of our records. The second thing it tells us is, if I were to allow n to be a bigger number, like let's say if I let n equal to 2, I'm only going to get bigger angles. It's not hard to see that that's true. The problem is, if these angles, when n equals 1, are already too big, that means that letting n equal 2 is going to give us even bigger angles, which will also be a problem. This means that if I choose any value of n bigger than 1 or equal to 1, we're going to get issues. So I'm going to go ahead and cross these out of my consideration. They are not going to be considered. We haven't tried negatives, so we may as well go ahead and try negatives. Let's see, if n equals -1, we're going to start out with theta equals pi over 3. We'll let n be -1 in this line, so that would be minus 2 pi. Oh, but wait a second. 2 pi is bigger than pi over 3. So when I subtract 2 pi from pi over 3, I get a negative. That's not in the interval that I'm interested in. It's smaller than 0, so this is a problem. And actually, if I do 2 pi over 3 minus 2 pi, which would be the next one we would get, it's also going to be a problem. It'll also be smaller than 0, so neither of these can be considered. At this point, I imagine that you can figure out what's going to happen with my answers from the blue system. The first one, of course, is out. The second one is the one that comes the closest to being included in our system. After all, 5 pi over 3 is very close to 2 pi, but once again, we're getting a negative number. Once again, we are not going to be considering this collection of possible answers because it doesn't fall into our interval. Once again, because we know we get a problem when we let n equal -1, you're going to get similar problems if you let n be equal to -2, or -3, or -4, or any of the other negative whole numbers. Therefore, we can simply stop searching in this direction, we can cross it out of consideration for us, and we can turn our attention only to the first bunch of possible solutions we got, the ones where n equals 0. We can finalize our solution set right now. The solution set should be pi over 3. Doesn't matter whether we take that from the red answers or the blue ones. Then we'll go for the next biggest angle, which would be 2 pi over 3. And finally, not including any repeats, we have 5 pi over 3. And this would represent all possible answers. Interesting. Now, you'll notice that this problem began already factored. You're not always going to have it so easy. Sometimes you're going to have to factor it yourself or figure out another way around. So let's go ahead and do another one. What we're looking at now is a much more interesting situation where we're given something that looks like a quadratic equation using cosine. There is an easy way to approach this. Well, actually, let me go ahead and say, to be more precise, there are two easy ways to approach this, both based upon the same basic observation. And it goes something like this. When I look at this problem, what I should do is I should mentally compare it to the situation where instead of writing cosine, I write x. Meaning that when I say cosine squared, what I really would be writing down is x squared. So what I'm doing is I'm comparing this equation that I've got that I want to solve in 0 to 360 degrees. I'm going to compare it to 2x squared minus 5x plus 2. Once you see it written out as a quadratic equation that is a little bit more familiar, you should realize that there are two possible ways to go. One of them would be to try to factor this problem out, and the other would be to use the quadratic formula. I'm going to go ahead and do both, starting with factoring. In my opinion, factoring is a nice, fast way to do things, and I always recommend you try it first. But I want to do both, just so you can see both. With that said, let's go ahead and try our first approach. Now, if I were factoring something like 2x squared minus 5x plus 2, an easy way for me to do that would be to start writing it out as something in parentheses times something in parentheses, and then figure out what I can about these parentheses that doesn't require a lot of effort. So, the first thing that I notice is the last term, which would be constant times constant, is 2. There's really only one way for that to be possible, since 2 is a prime number, and that is for one of the last numbers in my parentheses to be 1 and for the other to be 2. The next thing I notice is I'm getting 2x squared, well, for us really 2 cosine squared. I expect that I'm going to have cosines inside both of these pairs of parentheses, and using similar logic, it makes sense to me that one of them should be 2 times cosine, and the other one is probably going to be just cosine. Finally,
As I'm looking at what I've got here, I notice the middle term is minus, it's a negative, but the final term is positive. That suggests to me that I should have a minus sign in both pairs of parentheses. You should go ahead and double check me just to make sure that I'm not making a mistake, but it looks to me, just based off of that observation, that I should be able to say this is like solving the equation 2 cosine of theta minus 1 times 2 cosine of, or excuse me, times just cosine of theta minus 2 is equal to 0. And we just had an entire exercise on how to do something like this. The first piece, I'll go ahead and do this one first for my own nefarious purposes, should lead me to believe that cosine of theta minus 2 is equal to 0, or equivalently, cosine of theta must be equal to 2. Well, I can stop that one right there. There's absolutely no need to continue. I know already this one is not going to be true. So I can just cross that one out and move on to the next piece. The next piece would lead me to 2 cosine of theta minus 1 is equal to 0. And, of course, this will simplify down to cosine of theta equals to 1/2. That one we can solve. So we start using our information about working with systems of solutions. Since it is cosine, we know that we should wind up with something like theta is equal to, and we'll get 2 lines. Now, because we're working on a more complicated problem, I'm going to assume that you can do the basics yourself. So please go through, if you have to pause the video, figure out what angles I'm going to say before I put them down. Test your knowledge. I'm going to assume that you've done that. I can go ahead and tell you right now. The first angle I should get is pi over 3, because cosine of pi over 3 is 1/2. And then I should be adding, oops, now wait a second. I said 360 degrees here. That shouldn't be pi over 3. Ah, my love for radians is showing. 60 degrees plus 360 degrees times n. And that would mean that our second answer would be something like 300 degrees plus 360 times n. Actually, this is enough to figure out what our solution set should be. Our solution set, if you are Sean Connery or me having some kind of stroke, the solution set should be 60 degrees for one answer, and for the other one, 300 degrees, since clearly all the rest of them are going to be outside of the interval that we are interested in. Now we can do it the other way we promised. So, starting out with the slightly rewritten equation, I can go ahead and apply to this the quadratic formula. So, going through and writing some labels down just to help us, the lead coefficient is A, the middle coefficient, including the negative sign, is B, the last coefficient is C, and so we have a formula. We will fill in the gaps in that formula in just a second according to what we've written up above, but it's always given by x equals negative b plus or minus the square root of b squared minus 4ac, and all of this divided by 2a. In our particular case, that means that we are going to be taking the negative of negative 5, so that would be positive 5. We're going to be either adding or subtracting the square root of negative 5 squared minus 4 times 2 times 2, and then the whole thing is going to be divided by 2 times a, which means 2 times 2. From this point onward, for just a little bit, I assume that you guys can do the simplification. It really is just a little bit of arithmetic, so I'm going to rewrite it as follows, and I'll let you check my work. We should be getting 5 plus or minus 3 divided by 4. And this is going to lead us to two possibilities. One of these possibilities which I will put over here, is that x is equal to, let's go ahead and make it when we use the negative. So that'll be 5 minus 3, which we on Earth would call 2, divided by 4, which gives us a simplified version of x equals 1/2. Or, if we go backward and remember what we were substituting with, we said x means cosine, so what we're really saying is cosine of theta is equal to 1/2, which is exactly one of the equations that we got last time. I bet at this point you can guess what's going to happen in the next one. I would say to begin with, okay, x is going to be equal to what happens when we put the positive sign in the middle, so that would be 5 plus 3, which is 8, divided by 4, which would give us 2. And unfortunately, that simplifies to cosine of theta is equal to 2, the equation that didn't work, the one that we crossed out. Once we've done this, we realize that we actually have reached a common point in both solution methods. Once we've identified which equations we should be solving and which ones we are going to ignore, we simply go back to the methods that we showed to finish off the previous side of this problem. After this, whether you choose to factor or whether you choose to use the quadratic formula, everything becomes the same and we will get the same answers. But the fun doesn't stop here. Let's do another one. We wish to solve the equation root 3 sine of theta plus cosine of theta is equal to 0, and we wish to do this in 0 to 2 pi, so back to my beloved radians. This one is going to present an interesting challenge because now we are using both sine and cosine together. So, here's my recommendation about how to approach this. Sine and cosine, I don't know exactly how to relate to one another nicely. However, if you remember, we have a nice property called the Pythagorean identity, which looks like this. For any angle theta, cosine squared theta plus sine squared theta is equal to 1. So my nefarious plan here is to somehow work this problem to a point where I'm dealing with squares of sine and cosine, and then maybe I can use this identity to rewrite the problem and make it a little bit easier. First things first, though, I can't have them on the same side. You might think to yourself, I can just square the problem as written. But if I square the problem as written, I'm going to run into some ugly things that I really don't want to have to deal with. So I'm going to move things around to make it easier. I'm going to take the original equation, root 3 sine of theta plus cosine of theta, and then I'm going to subtract cosine to the other side. Now that sine is on one side and cosine is on the other, I can just go ahead and square this equation that I've wound up with, and it should give us some good information. Notice the hesitance in my voice because we are going to have to pay for this choice in just a little bit. For right now, though, if I square the left-hand side, it looks like we should get 3 times sine squared of theta is equal to, I square the right-hand side, it goes from being negative cosine to being just cosine squared of theta. And I see what to do from here. This isn't so bad. Using the Pythagorean identity, I can rewrite the right-hand side. I can make cosine squared into 1 minus sine squared. This is much nicer because now what I can do is combine like terms. Actually, I'm going to go ahead and move everything back over to the left-hand side because if I do, I'll be subtracting negative sine squared, so that means I should wind up with 4 sine squared. And then I'll be subtracting 1, and the result will be equal to 0. The left-hand side of this equation can be factored using the difference of squares. So I'm going to simply apply the difference of squares factoring here to get my 2 factors, which should be 2 sine of theta minus 1 times 2 sine of theta plus 1. And now we can use that zero factor property that we've been using in order to get more solutions out of this. I've put the solutions down below. I trust you guys can find them. And I'm going to make an observation. This will just make our lives easier. Note that sine of pi over 6, that would be 30 degrees if we were in degrees, is equal to 1/2. And this will probably tell us what we need to know to finish off this problem. If I draw this as a picture, just very, very quickly, this branch, sine is equal to positive 1/2, suggests to me that I should be looking at answers in quadrant 1 and quadrant 2, thanks to the reflection property. This second one here suggests that we should be looking at answers in quadrant 4 and quadrant 3, again using our reflection properties. I know that a reference angle for every single one of these angles should be pi over 6. And I also know that I want to represent our solution systems using positive angles. So I'm going to get two systems of solutions. Once we have these two systems, as before, we would choose different values of n in order to make this work. I'll let you double check what I'm about to say here. I think it's important that you check a lot of what I say to understand it on your own terms. But it seems pretty clear to me, just based on how I've drawn this picture, that n equals 0 is the only value of n that's going to work. And if I use n equals 0, what I would come up with for solutions should be theta equal to pi over 6, 5 pi over 6. I know the top row over here in the system says 11 pi over 6, but let's go in increasing order. It would then be 7 pi over 6 and 11 pi over 6. And that just looks so nice. Almost too good to be true. In fact, it is too good to be true. It's not obvious from what we've done right here that some of these just do not work, but some of them just do not. In fact, we should go ahead and test them all really quick so you can see what I mean. Now, this looks like it's going to be painful, but don't worry, since they're all based upon pi over 6 as a reference angle, as you can see in our picture, the only thing that changes from one line to the next is which function is positive and which is negative. So, starting with the first one, we know that sine of pi over 6 is equal to 1/2. So the first term should give us root 3 times 1/2, or in other words, root 3 over 2. Cosine of pi over 6 should be root 3 over 2, since sine of pi over 6 is 1 over 2. Oh, but look, that's not equal to 0. Our equation was root 3 sine of theta plus cosine of theta should be 0. We didn't get 0 for this one. For the next one, sine is still going to be positive. We're in quadrant 2, so sine of 5 pi over 6 and sine of pi over 6 are the same thing. So we'll end up with root 3 over 2. However, cosine in quadrant 2 is negative, so we'll get the same answer, except it will be a negative instead of a positive. This one is equal to 0, so that one's not okay, but this one is. In quadrant 3, now both of them should be negative, so we should get negative root 3 over 2, and then minus root 3 over 2, and that is not equal to 0, so that one's out. And finally, in quadrant 4, sine is negative, however, cosine is positive. That is equal to 0, so this one is okay. So actually, based upon this work, our solution set is not all 4 of the angles that we identified. It's only 2 of them. One in quadrant 2, 5 pi over 6, and one in quadrant 4, 11 pi over 6. Now you might be thinking to yourself, why the heck did that happen? What did we do that changed things? Well, the answer is back up here. Remember when we started out, we had an equation that looked like root 3 sine of theta equals negative cosine of theta? We squared both sides of the equation, and the negative sign that appeared on the right-hand side previously vanished. That negative sign was really important. The negative sign told us that when we were looking for answers, sine and cosine should not wind up being the same. One should be positive, one should be negative, or vice versa. They should not be the same sign. But when we squared, we no longer have that information anymore. You'll notice that when we look at the quadrants we indicated before we checked our work, we said quadrants 1, 2, 3, and 4. However, in quadrants 1 and 3, sine and cosine have the same sign. Said a little bit more carefully, in quadrant 1, they're both positive, and in quadrant 3, they're both negative, which shouldn't happen because of that negative sign in our original equation. By contrast, in quadrants 2 and 4, sine is positive in one of them, cosine negative, and the other, sine is negative and cosine is positive, which is what we would have expected. And indeed, when you look at our answers, the ones we kept were the ones in quadrant 2 and quadrant 4. This is actually kind of a quick way to see which answers are probably going to be right. If you keep your work careful, you keep your work neat, you can go back and look and figure out which solutions are likely to be thrown out. And now, I want to throw another quick curveball at you. This is the last problem that we'll do for this video, because otherwise I believe I'll make your heads explode. And the reason I'm throwing a curveball at you here, as I said, is notice our equation. 3 sine squared is equal to cosine squared. Well, if we go back to our previous page and look at our problem, we actually got 3 sine squared equals cosine squared in the course of our work. That may make you just a little bit suspicious and make you think to yourself, I bet you dollars to donuts we're going to be losing some answers just like last time. Well, let's see. Once again, we're going to start out with the original equation, the equation we were given. Before we do anything, and just like last time, we're going to be using the Pythagorean identity. If we do, and then we recollect terms on the left-hand side, we should get something that looks very familiar. So familiar, in fact, I've taken the opportunity to, first of all, factor it for us. And so familiar that I've gone ahead in a second step and found the solutions, or rather, I've used the zero factor property to get to the point where we can get our solutions. From here, there's no reason to beat a dead horse. We should get a picture like what we saw previously, what you see here on the left, and on the right we should get the two systems just like we did last time. All the work is the same. And it should lead us to the first answer that we got last time, that theta should be equal to pi over 6, or 5 pi over 6, or 7 pi over 6, or 11 pi over 6. This is where the shoe fell last time, so now we're going to go ahead and check it again. We might as well. This time, remember that we started with the equation 3 sine squared equals cosine squared, so let's go ahead and check that. You'll notice that I've chosen to calculate 3 sine squared and cosine squared on separate lines. That's because I want to check what each of the sides, the left and the right, give us, and then decide whether or not I'm getting a reasonable response. The other thing is, because they are squared, we no longer have to worry about positive or negative. All we need to do is square that number. So, for example, we know that sine squared of pi over 6 should just be 1/2 squared, which is 1/4. We have 3 times 1/4, so that should be 3/4. Cosine squared should be what happens when I take root 3 over 2 and square it, so that should be 3/4. Oh, they got the same thing. All right, let's move on to the next one. Sine squared of 5 pi over 6. Okay, we know that sine of 5 pi over 6 is 1/2, so we should be getting the same thing as last time. 3 times 1/4, or in other words, 3/4. Now, cosine of 5 pi over 6 was negative root 3 over 2. But since we're squaring that, we square a negative to get a positive, and we wind up with 3/4, just like last time. So that one's also okay. Last time, 5 pi over 6 was all right, but pi over 6 wasn't. That's interesting. All right, let's do the remaining ones. Let's see. In quadrant 3, that would be 7 pi over 6. Oh, they would both be negative before squaring. So after squaring, they're both positive. So we wind up with 3/4 and 3/4 again. And unsurprisingly, after all of the previous calculations, we get 3/4 and 3/4 again when we do the final calculation. So every single time, these work. You may be wondering to yourself, why is this different from last time? We have pretty much everything the same. What's the difference? Well, remember, this time we started out with 3 sine squared equal to cosine squared. We didn't get rid of a negative sign this time. Last time, when we began, we had to get rid of a negative sign when we did the squaring, and that's what changed our relationship. But this time around, no such thing happened. We started with squares. They were both going to be positive to begin with, so this time around, we don't have to restrict anything. This is exactly the correct solution set, so we may as well go ahead and write that down below. Our solution set, based upon our work, our best due diligence, is going to be all of the above. That's the worst set bracket I've ever drawn, but we're going with it. Pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Now, could we have known that all 4 were going to be solutions from the very get-go? Yes, you probably could with a little experience. When you realize that you have something that's guaranteed to be positive or 0 on the left and something that's guaranteed to be positive or 0 on the right, from that point onward, you can probably guess that you're not going to have to make any restrictions like we did in the previous problem. However, at the end of the day, the most important thing is that you can get the right answers. So here's my suggestion. Whether you get a problem like this one that we just finished, or like the previous one, my recommendation is the same. Try to see if you can figure out what's going to happen, but once you've figured out what's going to happen, in your opinion, then go in and actually check to make sure it works. It would be swell if you could just predict these things by looking at it. You probably will eventually get there if you keep working at it, but I'd much rather that you simply know how to get there, even if it takes you a little bit more work, than you try to aspire to some kind of nonchalance in mathematics. That's a big word for today. You got a vocabulary word and a math lesson. And speaking of the math lesson, that's all the time we have for right now. I think that's plenty of problems to get you started. Guys, I hope you had a good video. Please feel free to ask me questions, and I will see you in the next one. Until then, happy math. Bye-bye.